Okay, so today we are diving into the world of nanowires.
Nanowires.
Yeah, those microscopic wires that are going to revolutionize like
You,
everything.
you got electronics, energy medicine, you name it. We're talking building blocks 1,000 times smaller than a hair's width.
It's mind-boggling. And honestly, what's got me hooked is how they actually make these things.
Yeah.
This isn't like stringing beads on a thread.
Right.
We dove into some research from the chemical record, and let me tell you, it's like a whole new world of building.
It is. We're talking about gas phase synthesis,
Okay.
which the paper goes into.
Okay.
And so imagine that instead of carving something out, you're kind of essentially growing it from the ground up, using gases as your building blocks.
So we're not like carving a nanowire out of some bigger material. We're building it atom by atom.
Precisely.
Wow.
Traditional top-down manufacturing just doesn't cut it at this scale.
Right.
It would be like trying to create a detailed sculpture by chipping away at a giant rock with a jackhammer.
Right.
It's really about elegance and precision.
This is where it gets really interesting to me, at least.
Yeah.
The source mentions this VLS mechanism. What is that? Is that like a nanobot assembly line or something?
Not quite, although it does sound very science fiction-y.
Yeah.
VLS stands for vapor liquid solid.
Okay.
And the paper explains how it works.
Okay.
Picture a really, really tiny droplet of molten metal,
Okay.
like gold, and that acts as a catalyst.
Okay.
This droplet becomes super attractive to the atoms that we want in our nanowire.
So the molten metal is like a magnet for these atoms.
Exactly. The atoms dissolve into the droplet until they reach what's called a saturation point.
Okay.
And it's kind of like when you add sugar to water.
Okay.
At some point, no more sugar can dissolve and it starts to crystallize.
Right.
But in the case of nanowires, instead of sugar crystals, we get a nanowire sprouting out of this metal droplet.
It's like controlled crystallization with this metal droplet as the seed.
Yes, exactly.
And this VLS thing, it's used in a bunch of different nanowire growing techniques.
Absolutely. And that's what makes it so versatile.
Okay.
And the paper looks at chemical vapor deposition.
CVD?
CVD.
CVD.
You got it. And you can think of it like this. Imagine a high-tech oven where we can carefully control the temperature, the pressure, and what kind of ingredients we put in.
Ingredients meaning gases.
Exactly.
Yeah.
We introduce gases that contain the elements we need for our nanowire.
Okay.
And as these gases heat up, they decompose, they react with each other, and then guided by that VLS mechanism that we talked about, they start to deposit onto a surface, atom by atom.
Wow.
Forming our nanowire.
So we need a specific surface for them to grow on.
Yes, it's called a substrate.
Substrate.
You got to think of it like the foundation for our nanowire skyscraper.
Okay.
And this is where things get even more intricate.
Okay.
The type of substrate can actually impact the properties of the nanowire itself.
So we're not just dumping ingredients in an oven and hoping for the best. There's like
Right.
fine-tuning going on here.
Absolutely, a lot of fine-tuning.
Wow. The paper mentions two types of CVD, hot wall CVD and plasma enhanced CVD. Am I picturing like tiny little ovens versus high-tech microwaves or?
You're on the right track.
Okay.
It's all about how we deliver the energy needed to kickstart those chemical reactions and get those nanowires growing.
Okay.
Hot wall CVD is our reliable workhorse, kind of like a conventional oven where we heat the entire chamber to a specific temperature.
Makes sense. But then what's with the plasma enhanced version? What makes that so special?
Well, sometimes we're working with materials that are a little bit like picky eaters, I guess you could say.
Okay.
They don't always do well with too much heat.
So we can't just crank up the heat for everything.
Exactly.
Okay.
And that's where plasma enhanced CVD comes in.
PEC CVD.
PEC CVD, that's right.
Okay.
Instead of just relying solely on heat, we use what's called a plasma,
Okay.
which is like a supercharged gas, you could say, that can break down those precursor gases and get them ready to deposit onto the substrate without having to use as much heat.
Okay, so PECVD is like using a lower heat setting so we don't burn our delicate ingredients.
That's a great way to put it. And the beauty of PVD is that it's not just about protecting those sensitive materials. It also opens up this whole new level of control.
Okay.
The paper talks about how researchers can actually tweak the plasma conditions to fine-tune the properties of the nanowires.
Wow.
It's like having a set of high-precision knobs to adjust the size, the shape, even the electrical conductivity of these tiny structures.
That's wild. So it's not just about building these nanowires, it's about tailoring them for specific applications.
Absolutely. And the paper highlights a really good example. They talk about how PVD is used to grow silicon nanowires for next-generation transistors.
Okay.
And because PVD operates at lower temperatures, it allows these incredibly tiny transistors to be built on top of existing electronics without causing damage.
Wait, are you saying they can build these tiny components directly on top of the chips we already use?
Precisely. It's like adding a whole new floor to a skyscraper. But instead of steel beams, we're talking about components 1,000 times thinner than a human hair.
That's mind-blowing. Okay, I have to ask about this flame synthesis thing you mentioned.
Yeah.
Are we really talking about tiny blowtorches for nanowire growth?
It does sound a little wild.
Yeah.
But flame synthesis has actually been around for a while.
Okay.
It's been used to produce things like carbon black, which you find in everything from tires to printer toner.
Wow, I had no idea.
Yeah.
But I'm still picturing these scientists with tiny little Bunsen burners.
Well, it's not quite that rudimentary,
Yeah, okay.
but the principle is the same.
Okay.
We're using a carefully controlled flame to create the high temperatures needed to decompose those precursor gases and deposit the atoms onto a substrate.
Okay, so it's like using a more focused and efficient heat source.
Exactly.
But what are the advantages of using a flame over something like CVD?
Well, for one thing, it can be incredibly efficient and scalable. Think about it. You don't need to heat up this whole chamber like you do with CVD.
Right.
The flame provides a very localized and intense heat source right where you need it.
Okay.
This makes it incredibly energy efficient and potentially much cheaper for large-scale production.
So it's like the difference between using a campfire to boil a pot of water versus heating up your entire backyard.
That's a great analogy.
Okay, cool.
And the paper actually points to a really fascinating example of this scalability.
Okay.
They talk about how researchers are exploring flame synthesis for producing nanowires for solar cells.
Really?
Yeah, imagine being able to kind of spray on a coating of nanowires to create really efficient and affordable solar panels.
Okay, now we're talking about a game changer.
Yeah.
But let's move on to the last method mentioned in this research,
Okay.
which seems almost like the opposite of flame synthesis. This is physical vapor deposition, or PVD.
PVD, right?
Yeah, so less chemistry, more physics this time around?
Yeah, PVD is a different beast.
Ah.
Instead of relying on those chemical reactions to create our nanowires,
Right.
we're using physical processes to deposit atoms directly onto the substrate.
So tell me more.
One method that I found really interesting in the paper was molecular beam epitaxy, or MBE.
MBE.
MBE, you got it.
Okay.
Imagine this. We have a chamber with incredibly low pressure, almost a vacuum,
Okay.
and we heat up a source material, which could be a solid or a gas, until it starts to evaporate.
So we're essentially vaporizing our building block.
Precisely.
Okay.
These vaporized atoms then travel through this vacuum and land on our substrate.
Okay.
But here's the key. Because the environment is so pristine and controlled, the atoms can land and arrange themselves with incredible precision.
So we're laying down these atoms one by one, like building a house brick by brick, except our bricks are atoms.
Yeah, it's a good analogy.
Okay.
And the paper talks about how MBE is used to grow these really thin layers of materials for high-performance lasers and LEDs.
Okay.
We're talking about layers that are only a few atoms thick.
Wow. Okay, that's officially beyond my ability to even picture.
Yeah.
But back to nanowires for a second.
Okay.
If we're just spraying these atoms in a vacuum,
Right.
wouldn't they just create a thin film?
Right.
How do we get them to form those precise wire structures?
Well, that's where it gets really clever.
Okay.
Remember how we were talking about how substrates are so important?
Yes.
Well, in MBE, we can actually use what's called a patterned substrate,
Okay.
kind of like a tiny stencil, to guide the growth of the nanowires.
So we're basically giving those atoms a predetermined path to follow as they land.
And the paper calls it templated growth.
Templated growth.
Yeah, and it lets us create some really interesting nanowire structures. Zigzags, spirals, you name it.
Wow, okay.
And the paper actually highlights how researchers are using this technique to create nanowires for next-generation batteries.
Really?
Yeah.
Wow.
Imagine a battery where the electrodes are made of these intricately woven nanowires. You could potentially store way more energy in a much smaller space.
Smaller, more powerful batteries, sign me up.
Right.
It seems like each of these gas phase synthesis methods has its own pros and cons.
Yeah, definitely.
What are some of the key takeaways you're walking away with from this research?
One thing that I find really fascinating is just how much control scientists have over these processes.
Yeah.
We're talking about manipulating matter at the atomic level,
Right.
choosing exactly which atoms go where.
It's like having a molecular set of tweezers.
Exactly.
Wow.
And with that level of control comes just this whole world of possibilities.
Absolutely.
And the paper really emphasizes that this is still a very young field.
Okay.
But it's already yielding these incredible breakthroughs. And as these techniques become more refined and more accessible, who knows what we'll be able to do with nanowires in the future.
From flexible electronics to super efficient solar cells to targeted drug delivery, the possibilities seem endless.
Exactly. It really seems like the sky is the limit.
It really does. This deep dive has definitely given me a whole new appreciation for the power of the very, very small.
Yeah, me too.
Thanks for joining us on this journey into the nano world.
Happy to be here.
And until next time, keep exploring.